Maxwell had developed the theory of an entire family of electromagnetic waves. They all had the same basic form of an oscillating electric and magnetic field, and they all travelled through space at the same speed, which Maxwell had calculated to be about 3 by 10 to the 8 meters per second, which was known to be the speed of light. This meant Maxwell was able to explain what light and infrared radiation were actually made of. But the other result of his calculations was that even though these waves were limited to one speed, there was no limit to what their frequencies, and hence their wavelengths, could be. So he predicted that there were other frequencies of electromagnetic waves out there, but we didn't have any way of detecting them. Maxwell died before anyone found a way to do this, but in 1886, Heinrich Hertz became the first person to transmit and receive controlled radio waves. Hertz used the same type of induction coil that we learned about last week. It was a pair of coils, one inside the other, that acted as a step-up transformer, and a switch turned the current on and off at high frequency to get the changing current needed for the transformer to work. So the secondary coil was a solenoid, so it was an inductor, and there was a capacitor in the circuit as well. When you have both of these components in a circuit, then the circuit will oscillate. This is because the inductor and the capacitor both store energy, as we've seen. The capacitor stores energy as an electric field, and the inductor stores energy as a magnetic field. So, at the right frequency, the stored energy oscillates back and forth between the capacitor and the inductor with very little loss. So their effective resistance is very low at that frequency, and so that's where most of the circuit's energy will be emitted. The expression for the resonant frequency is omega, the angular frequency 2 pi f, equals 1 over root LC. So that if you know the value of your capacitor and your inductor, then you know the frequency that your electromagnetic waves are being emitted at. At the bottom of the induction coil circuit, you see a thing labelled transmitter. This is just a break in the circuit with a couple of spheres very close together. These are the electrodes, and when there is a pulse of high voltage between them, a spark will jump across the gap. This spark means that electrons are jumping between the electrodes, and therefore they're accelerating, and so they emit electromagnetic radiation. The next step in the experiment is to detect the electromagnetic waves. You'll notice that at the bottom of the diagram there is another spark gap called the receiver. The electrodes of the receiver spark gap are simply connected by a loop of wire, which completes the circuit. There's no power supply in the receiver circuit. However, when Hertz set this up, he found that when a spark was created in the transmitter spark gap, you could sometimes see a faint spark jumping in the receiver spark gap, even when the receiver was meters away from the transmitter. He concluded that some form of energy was travelling from transmitter to receiver, and so he set out to find the characteristics of that energy and prove that it was an electromagnetic wave. Hertz observed reflection and refraction in his electromagnetic waves, and he also found that they were polarized. We'll talk more about polarization in another lesson. Hertz's work culminated in making an interference pattern, which was a standing wave, with his radio waves, and using that to measure the wavelength, which could then be combined with his known frequency from the induction coil to calculate the speed of the waves. As he expected, it was very close to the speed of light. Have a look at the demonstration in the following video that will help you understand the experiment, and also see how you can run a classroom demonstration of the production and reception of radio waves.